Good afternoon, guys.
Good afternoon.
Go ahead and sign up for the attendance. Sign the attendance sheet. Today we are going to do some problems from chapter 7. That will cover our recitation, and also at 12:40, remind me if I was not paying attention, there will be quiz, and that quiz is on the blackboard. Okay? Yeah. So I shared the slides. You might be seeing the slides now. This is chapter 7, kinetic energy and work. This is the first problem from chapter 7. A 12 Newton force with a fixed orientation does work on a particle as the particle moves through the three-dimensional distance, which is given here. What is the angle between the force and displacement if the change in the particle's kinetic energy is plus 3J? Okay. Here in this problem, I need your input. How can we handle this? How can we solve this? There was a popular theorem that we used to work on. Can someone tell what that theorem was?
Dot product.
Dot product is one thing, and also, the other student, what you were saying?
The change in kinetic energy is equal to the work.
Yes, change in kinetic energy is equal to work. Change in kinetic energy is equal to work. And as the other student said that it is dot product, so basically he means that the force, the work here, it's a dot product. It's the dot product between the force and the displacement in the vector form like this. And since we know that A dot B is equal to AB cosine theta, so it is going to be FD cosine theta, okay? And here on left side we have KF minus Ki, but since they already given us the change in kinetic energy, so we don't need to split this up, okay? Just we keep it as it is, like this, delta K. Okay. Now they're asking for the angle between the force and displacement. We know that the angle is appearing here in this problem like this. So we need to make the arrangements, divide both sides by FD. So it will be cosine theta equal to delta K divided by FD. And then I need the angle, so I will take the cosine inverse of the both sides, and it will be delta K divided by FD. So let's understand the delta K is given, which is 30 joule. We also know the magnitude of the force is given, which is 12 Newton. The D, it is given in the unit vector notation. So we have to determine the magnitude of this, okay? So I'm just putting it like this, cosine inverse, it is 30 joule divided by 12 and times the magnitude of the D, and it will be 4 plus 16 plus 9, okay? So this is all. Once you put this in your calculator, you will get an angle for this. That is your answer. And part B, they're asking, what if the change in kinetic energy was minus 30? All you need to do is to replace this 30 by minus 30, and you will get a different answer for the angle. Okay. Let me know if you need any explanation at any point along the problems. Okay, this is another problem. It appears in Major 2-171. A helicopter lifts a 60-kilogram astronaut 15 meters vertically from the ocean by means of a cable. The acceleration of the astronaut is G divided by 10. G is 9.8 divided by 10. Vertically out. How much work is done on the astronaut by the force from the helicopter? Consider the initial speed of the astronaut is 0 and ignore air resistance. So when the cable is coming to the astronaut is lifted up. Okay, so what will be the force acting on the astronaut upward. What is the upward force on the astronaut?
The tension.
The tension force, yes. So here we need to look for the tension force. Consider this is like the astronaut. We know that the astronaut has some weight which is downward. We also know that there is a cable attached to the astronaut, and in that cable there is a tension force upward. And they are saying that the astronaut was left out. So means the acceleration produced in astronaut is upward. A is upward. So now I'm putting in the form of the equation. Okay, I need this tension force to know it, because what I want is that the work done by the tension, you know, it is T D cosine theta. So D is the displacement covered upward, T is the tension force, angle is the angle between the tension and the displacement. So the thing which I don't know is the tension. Can someone tell me how to formulate the tension force from this diagram?
You can say that tension minus mg is equal to ma.
Okay, T minus mg is equal to ma, because tension and acceleration, both of them are up. We are taking this positive. Mg is downward. We are taking it negative. So I'm rearranging this equation for the tension moving the mg to the right side. It will be ma plus mg. Okay, and we know that as it is given in the problem that this a is g divided by 10. So we can just put it like a g divided by 10. Okay, m g, you can just take it like this. You can take mg common, and it will be 1 divided by 10 plus 1. Okay, which is giving us 11 divided by 10. 11 by 10 is 1.1. So if I know the mass of the astronaut, just let me put it. No need to speed up. Okay. So from this, we are putting the tension, and tension is this one, right? We know that it is mg. It will be 11 divided by 10, which is 1.1 times mg. So 1.1, okay, times mass of the astronaut, that is 60 kilogram, g is 9.8, and the displacement cover upward, that is 15 meter. That is 15 meter. And the angle between the displacement and the tension, what is the angle?
0.
180.
90.
Yeah.
180.
Why 180?
I think 0.
0.
Zero because that is parallel to each other.
They are parallel to each other because the astronaut was moved up. So you always look at the direction in which the object is moved. So if the object was moved upward, this is the direction of the displacement, okay? And we also know the tension in the cable is also upward. So therefore, these two are parallel, and we are getting the angle 0. So cosine 0 is equal to 1. So you have the numbers, you can calculate afterward. Okay. Any question here?
Wait, teachers, is the distance? It's over the ocean, not the length of the string. Am I right?
It is the length of the string up the as it says that a helicopter lifts a 60 kilogram astronaut 15 meter vertically from the ocean. Okay, so it means the ocean is here and the helicopter up there. So the person will go from here upward like this. You got it? So it is above the ocean level. Yes.
Another question. Isn't work only done horizontal, like horizontally?
No. Work can be done horizontally, or it can be done in any direction in which the force was applied. Because by definition, you remember that if there was a block and there was a force applied, the displacement supposedly should be covered in the direction of the force. Okay, so if this is the force, this will be the displacement. If the force happened to be applied with some angle like this, you remember that we just take the cosine component of this, which is the f cosine theta, because f cosine theta is parallel to the displacement. This is the only component of the force that works. The f sine theta, it is perpendicular to this. It cannot do any work along the horizontal. Got it?
Kinda.
Yeah. Okay. We can explain it. Yes.
Doctor.
Yeah.
We found the tension. So should we multiply it by the displacement to find the WT?
WT, we are doing this here, right? You see, this is the formula. This is the T times D and cosine theta. So the T which we found, it is mg 11/10, which is 1.1. So I put 1.1 here, mass and g. And then I multiplied this 15, which is the displacement right here. And then the angle I took between the T and the D, which is 0, because both of the forces, the displacement and the force are parallel. That's what I took.
Sorry, what is 1.1? What is it?
It is coming from the tension, because you see the tension is from
Yeah.
Okay. And the acceleration is 9 g/10.
Okay, I get it. Thank you.
Another problem, guys. It also appeared in Major 2 exam. A 25 kilogram box is initially moving with a velocity that has magnitude 3.5 meter per second in a direction 37 degree west of north. How much work must be done to change its velocity to 5.6 meter per second in a direction 63 degree south of east? So let's put the diagram first. I know this will get a little bit, there is a little bit confusion, so I will try to clarify that as well. Okay, initially, the object is moving with a velocity that has magnitude 3.5 in a direction 37 degree west of north. So you know this is north, this is east, this is west, this is south. West of north by that many degrees, so there is 37 degree, and you need to pass this vector for that velocity, and that is V initial. Okay. Now, how much work must be done to change its velocity to 5.6 meter per second in a direction 63 degree south of east? South of east. Here you take the 63 degrees, okay, and then you pass this one. So now, afterward, finally the object goes in that direction. Now they're asking how much work is going to be done. Can you guys comment on it? How can we easily determine this work?
The delta of kinetic energy equal to work.
Yes. Delta K is equal to work. They're asking determine work. I'm going to look for the kinetic energy. It is Kf minus Ki. Here we have half mVf square minus half mVi square. Now the confusion is that if I want to determine the work, the easy method for me is I will take this half, mass is 25, final speed is 5.6 meter per second, minus half, again 25, and then initial speed was 3.5 meter per second square. And this will give me work. I don't need to do anything else with this.
What about the direction of the speed?
That is a confusion, yes. The direction is.
But
Here-
does the work is a scalar?
Yeah, the work is a scalar quantity, yes. So you see this is the scalar quantity. You can see the work from the F dot D. F dot D. When you see the dot product, it means the result of the two vectors product is going to be scalar quantity, F D cosine theta. That is a scalar quantity. Okay, regarding the direction, guys, here you have this initial speed, and if you want to determine the x and y components of it, you can do so. Like it will be VI x, and here you will have VI y. Okay. Then how do you determine the speed here, which is the initial speed, which is the VI square, right? So VI square, you will go with the components like VI square is equal to VIX square plus VI y square. And we know the V is equal to VI cosine theta and VIY is equal to VI sine theta. So VI is a common thing that factor, I will take it out, and I will left with the cosine theta plus sine square theta. So cosine square theta plus sine square theta, what do we get?
1.
1.
1.
So we got 1 from the right side. Okay? So which tells us that the VI square is equal to VI square, which is of course quite obvious. So if you go and split this entire problem in components right there for the initial speed as well as for the final speed, and you want to determine the initial speed square and the final speed square, at the end you are ending up at the exact same answer as we put here. So you are just adding the trouble. You don't need to go there. All you need to do is to look at the initial speed and the final speed, and since the kinetic energy uses the magnitude of the velocity, so you don't need to split this in components. Don't need to go into the components. That's all. Okay. A spring and block are in an arrangement as shown in this figure. When the block is pulled out to x equal to 4 centimeter, we must apply a force of magnitude 360 Newton to hold it there. We pull the block to 11 centimeter and then release it. How much work does the spring do on the block as the block moves from xi 5 centimeter to x equal to 3? And also other options are given, like 4 different options are given, but the block begins from xi. So let me write the equation for the work, and then if you recall the equation for the work done by the spring, can you tell me that? Work done by the spring. What is the equation for that?
F equal to kx.
Minus. There's a minus.
There is a. This is here we are talking about the work, not the force. Okay, we begin with the work. So in the work, it will be half k xi squared. Notice here, xi squared minus half k xf squared. This is the work done by the spring. And the spring force, it is minus kx by the Hooke's law, the spring force. This is equation 2. Just by looking at this equation 1, they say that how much work is done by the spring if the spring goes from xi, which is 5 centimeters, to xf, which is 3 centimeters. So xi and xf both are given, half is constant. The only unknown right here is k. How can we determine k?
By the
From the second equation.
From the second equation. But in the second equation, look at this, okay? This is always the confusion part, which is the minus point here. This is the spring. The spring applies a restoring force in this direction. The problem statement says that when we pull the block to 4 centimeter, we must apply a force of magnitude 360 Newton. 360 Newton in this direction, okay? So this is your applied force. We know this and this force are in opposite direction. So if I'm comparing the Fs with the applied force, I should apply the negative sign here, okay? And for the Fs, I'm putting this minus Kx. Minus Kx equal to minus Fa. So the minus will go with the minus. So the K from here is equal to Fa divided by the displacement. So you applied 360 Newton force, 360 Newton force, and you are able to move the block by 4 centimeter. So 4 times 10 to the power minus 2 meter. This one will give us K. If you can give me the answer for the K, then I can put it here.
9,000.
9,000. So 9,000, and also note the unit of the K. It is Newton per meter. Newton per meter. Okay, so 9,000 Newton per meter. Now at the end, whatever at the middle it says, it's not needed. Let's jump into the very last statement. How much work is done when the spring moves the block from xi, which is 5 centimeter, to xf, which is 3 centimeter. So we will put those in this formula, those quantities. So K, we can take it out. Half and K, we can take it out. So we put for the K 9,000. And inside we left with the xi, and that was 5 centimeter times 10 to the power minus 2 square minus, and the xf is 3. Okay. This one will give us a work. For the part B, part C, part D, all you need to do is to just keep changing the 3 to minus 3 to minus 5 to minus 9. All you need to do this. So I will leave that to you. Do you have any question here?
I have a question about the work of spring.
Okay.
If the energy was stored in the spring,
yes,
the work will be positive or negative?
Here we are talking about the two things, okay? Here we are discussing the work done from the perspective of the work done by the spring force, not any other form of energy stored, okay? This will come into the next chapter. Okay. But if you are interested to know that, yes, when the spring goes to one end and another end, we know that it momentarily stops there, but the energy is there which stay in the potential energy form. When the block comes into the middle, so at the middle as the block passes, it has highest speed. So at that point, it has the maximum kinetic energy. So this energy always convert from the kinetic energy to the potential energy and vice versa. If there was conservative forces involved and no friction, no air resistance, then the block will oscillate forever and the total mechanical energy will be conserved. But that is the topic to be discussed in chapter 8.
Thank you.
Yeah.
A and B will be the same, right? In the previous question.
And A and B is the same, exactly, because the minus sign doesn't matter because it's a square term, so the minus sign will be absorbed. This is if you remember that I solved a problem by integration area under the curve. So this is one of the problem for the area under the curve, because we are now dealing with a variable acceleration, and for the variable acceleration, the object covers some distance. So let's read the statement of the problem and understand how can we solve this. This figure gives the acceleration of a 2 kilogram particle as an applied force moves it from the rest along an x-axis from x equal to 0 to 9 meter. The scale of the figure, vertical axis is set by AX. AS is 6 centimeter. So the maximum AS scale, that is 6 meter per second square for the acceleration. How much work has the force done on the particle when the particle reaches to x equal to 4 meter? So you see that in this figure, when the particle goes from here to here, 4, we need to look at the acceleration. This will be the corresponding acceleration at that point. But the acceleration was not constant all the time, because here the acceleration was continuously changing in this part and it is constant in this part. So when we want to determine the work done by the this force which creates this acceleration, what we need to do is to apply the very basic equation of the work done. So work done is equal to F. You can say S or X or delta X, whatever you choose. So you can say delta X if you just are interested in that. Delta X. F delta X. Okay. Since this force, we know it is acceleration involved, so it's the Newton's second law type force. Here we have the M and acceleration A delta X. Now look at the graph. The graph on the y-axis we have acceleration. On the x-axis we have delta X. M is not given. So if we multiply this with the, like when we get this area under the curve, it is not necessarily the force versus the X, but the area under the curve will be for the A times a delta X. And whatever the area we get, when we multiply this with the mass of the block or mass of the particle, then we will get the total work done. So here we have the mass, that is 2 kilogram, times area under the curve. So if I'm going from x equal to 0 to x equal to 4, how can I determine the area under the curve here?
So we can divide it, the area under it.
We can divide the area. So how to divide that?
To one there's a triangle.
One will be a triangle, which is this part here.
Yes, and this is a square. So,
and the rest of the part looks to be a square, which is a rectangular type, right? Okay. So here we need to determine the area for the triangle. Area of the triangle is half base. Base is here, which is the 1 and times 6. So 6 times 1. This is one area under the curve. The other one will begin from the 1 all the way to 4. So 4 minus 1 is 3. It will be 6 times 4 minus 1, okay, which is 3. Now I'm getting this 2, just remove the kilogram from here to remove the confusion. We have 3. We get 3 from here. 6 times 3 is 18, plus 3 is 21. So 21 we get. 21 times 2, it is 42. So 42 joule of work is done while the particle is going from x equal to 0 to x equal to 4. Any confusion here?
It's clear to me.
Okay. Okay. Now, when you go to x equal to 7, the everything remains the same, because now you have one triangle for that, another rectangle for that, the second triangle for this, okay, from here to here. And then when you have the x equal to 7 like this, then you again split this into 2 geometrical shapes. One geometrical shape will be this, like this, which is that rectangle, right? and this one is triangle. So what you need to do is one triangle, second triangle, and third triangle, and one rectangle and second rectangle. But for this case, which is above the x line, that is positive, and which you get below the x line, x-axis, that is going to be negative because the acceleration is negative, so you will get negative sign here. So you need to add and subtract accordingly and get the total work done by the variable force.
Doctor,
Yes.
if the acceleration, for example, was force, so the area under the curve will be the work?
Yeah, will be the work. You don't need to multiply this mass afterward.
Ah, okay.
Yeah.
Doctor, here we got the force first, and then we want to multiply it by the distance, don't we?
Yeah, if you want to proceed in that way, yes, it's no problem. All you need to do is that you determine the total force, which seems to me a little bit lengthy, but if you are interested in that, yes, you can always do that. You multiply the acceleration component, which is 6 here, by 2, which will be 12, and then you multiply it with the displacement. And of course, always use the formula for the right geometrical shape. If it was triangle, a triangle, then the half will be coming from the triangle area formula. And if it was square or rectangle, then you don't have any half in there. You just multiply side by side. But this is the simple method for them. Just look at the area under the curve.
Okay, thank you.
Doctor, I have a question.
Yeah.
Under the x-axis, what to do?
It is under the x-axis. You see this triangle. Let me calculate for this one. Okay, this triangle you see here. This triangle, the method remains the same. Everything remains the same. But what you do is you have mass, which is 2 kilograms, and then you are again multiplying a times x, right? But now you have this triangle, so half is coming just from the triangle area, and the acceleration component, which is here, which is the perpendicular side of the rectangle, the triangle, which is -6. So you have -6 here, times the base of the triangle, which is from 5 to 6. So 6 minus 5 will give you 1, right? So from here, you get 3. So -3 you get from here times 2, which will be -6. Okay, -6.
Okay, clear, Doctor. Thank you.
Yes. Okay. This is another problem, guys. Here we are jumping towards the very last topic of the chapter, that was about the power. At a certain instant, a particle-like object is acted on by a force which is given here, while the object's velocity is this much. What is the instantaneous rate at which the force does the work on the object? So here, pay attention to it. It is not asking for the work, but rather it is asking for the instantaneous rate. Okay, and the rate would mean here you are the work done per unit time. So power, instantaneous power, you can see it is work done per unit time, like dW by delta T. So this is the work done by time, and it is also written as, since it is instantaneous power, it can be written as F dot V, just the dot product of the two. So you know, here you have the force, which is given in the 4I minus 2J plus 9K dot with the minus 2I and plus 4K. Okay, this is the velocity. Now, when we take the the dot product, we know this term and this term, I times I will survive. So it is 2 times 4, which is -8. And here you have 4 times 9. How much it is?
36.
36. So 36 minus 8. What do we get?
28.
28 joule per second, or 28 watt, because joule per second is equal to watt. So this is the instantaneous power we get from the velocity and the force. Now, in the second part, they are saying at some other time the velocity consists of only y component. If the force is unchanged and the instantaneous power is -12 watt, what is the velocity of the object? Can you help me in that? How to solve that?
I think the same formula.
Okay.
Then we have the power instead of finding the power.
Okay. Here, what they are indicating, they are pointing to a very good important characteristics here. You say they are saying that the velocity consists of only y component. If velocity consists of only y component, you will be able to pick only the y component of the force. Because the dot product, it only looks for the similar components in the two things, the two vectors, right? So therefore, when I'm taking the power, like just write the power like this, and you say Fy Vy, because all cross components or any other components will be 0, because the components in the velocity does not exist. So it will be like this. Now, you want this this component of the force, which is -2j. -2 is the y component of the force times Vy. Okay? And as it is given in the problem that the power is equal to -12. -12 watt is equal to -2 Vy. Minus will cancel with minus, 2 with cancel here, so it's giving us 6. And also, of course, it is Newton, so it will cancel out the other units, and we will get it is a 6 meter per second. Okay. Since they're asking for what is the velocity, not the speed, so by component we already got it is 6 meter per second. But by velocity, what unit vector should I put here?
J.
J. Okay, so when I'm writing it and the velocity, I will remove this y component. It will be the velocity like that, and you have only J. This is on.
Doctor, now is the time for quiz.
Okay. What the time?
38.
38.
2 minutes left.
2 minutes remaining.
Okay. 2 minutes. Okay. Let me comment on this one. A loaded cab of an elevator has a mass of this much, 3 times 10 to the power 3 kilogram, and moves to 10 meters up the shaft in 23 seconds at a constant speed. At what average rate does the force from the cable do work on the cable? So this is again what, when you look at the statement of the problem, they're asking for the average rate, which is actually they're asking for the power. Okay. So I don't want to hold you here. You can go ahead and log into your Blackboard account, wait for the quiz to appear, and begin the quiz.
Doctor, it's in the assignment?
It is under assignments, yes.
Mister, should I write the units or I don't have to?
You don't have to.
Teacher, we finished the quiz. Can I leave?
Yes.
Okay.
Doctor, do I have to write kilogram or just the number?
Just number.
Okay. Thank you.
Doctor,
Yes.
when is your office hours?
Right now, after this class.
Okay, I will come. Thank you.
Okay.
I finished. Can I go?
Yes.
Thank you.
Yeah.
Thank you.
What's that?
Should I write it in scientific notation, the numbers?
No, general form.
Oh, okay.
Yeah.
Right done, sir.
Okay.
Can I leave? All
Yeah,
right.
sure. Students who are done, they can leave. Yes. Class.
Before I leave, I have a question about the attendance. How can I know my attendance schedule?
When do for the some attendance I had uploaded to Blackboard, so you can see it there. The later one, when I upload them, you can also see. But if you ask specifically for some attendance, then I can provide you that.
No, not specifically, just generally. How many absences do I have?
You can look at the date on which I had uploaded on the Blackboard. Up to that date, it will show your absences in there.
All right, thank you, sir.
Teacher.
Yeah.
I submitted before the time ends, but he gave me late.
No worries. No worries.
Okay.
Doctor.
Yeah.
Can I leave, doctor?
Sure.
I forgot.
You can leave. You are done with it. You can leave.
To fill the attendance form. Can you open it for me?
Jafar?
Yeah, I'm Jed.
When did you join the class?
From the start, but I forgot it.
Let me see if I want you.
Me too, that. About the test says points possible. Does that mean I have and give me late?
Okay. So students have joined earlier. Okay, I can open that for you.
Excuse me, doctor.
Thank you.
I submitted my quiz in 9 minutes and it said it's late.
No worries. This is every time I'm explaining this. The late doesn't mean anything here. As long as you have entered your answers before the due time, then you're fine. Okay, go ahead and put your attendance there.
Okay, thank you.
Yeah.
Doctor, when it says late, is there a way I can see?
What is that?
When Blackboard says I'm late.
It's fine.
Yeah. Is there a way I could see my grade?
Your grades?
Yeah.
It will compile when you submit your grades now. You mean you're asking for all the grades or just for this quiz?
For this quiz.
For this quiz, it will take like half an hour or so for the Blackboard to compile all the information and assign the grades.
Oh.
Yeah. Yes, Musab.
Yes. Can I know what's the true answer of the second question in my quiz, or I can't?
I think let's just wait for that because I need to go over this. You can ask in the next office hours if you want.
Okay.
I need to go over all the quizzes now and look at the grades. If the grades were assigned, fine, then yes. Yeah. Do you have any other question?
No, just this question.
Okay, any other student who wants to ask questions or you need any help in something?
Doctor.
Yeah.
I put the wrong answer and the quiz, and you know now the.
Okay.
Can I send you my solution in the email?
You can you can send me your solution and I will see if there was a little bit difference just because of the significant figures at the points or something, then I can correct them. But if there was something else, then we can talk later about that.
No, it was the multiple choice question.
The multiple choice question, this is gone because if I accept it after the quiz now, then I have to accept for all students, and all students can claim.
Yes.
Yeah.
Thank you.
Yeah, no problem. Okay, looks like you don't have any question for me.
I have one question.
Okay.
With the homework from chapter 6, I think.
Okay.
The second question about the Wheaties, I think it was called.
Okay, let me get into the Wiley Plus, right?
Yeah.
Please send me your ID in the comments.
Oh, no,
what
no.
is,
I got the grade. It's just that something I don't understand in the question.
Okay, tell me that.
The way that we did the solution, I was wondering why couldn't we solve it in another way? Do you have the question right now, Doctor?
I don't have the question. I need to get into it. Just send me your ID so that I can see specifically different layer of questions.
Oh.
Yeah. Okay. And your section is? 28, 9, 29, or 30?
28.
28.
By the way, for today's quiz, Doctor, didn't we decide we'll make it tomorrow?
It was not decided. A student asked for that in section 28, and then I asked in the other section, and the section was the majority decision was that they were in favor of the today's quiz because, of course, the midterm exam pressure is building up now.
Yeah.
Yeah. So then I just stick with the same decision, and since this was only discussed in section 28, a student requested, so I sent an email via Blackboard to section 28 just to reconfirm that today the quiz is today. Okay, which question you are? Question 1, 2, 3.
2.
Okay. Okay. Here, this figure, a box of Cheetos. Cheerios mass. Okay, 1.4 kilogram in a box of Wheaties. It's another thing. Are accelerated across horizontal surface by a horizontal force applied to the Cheerios box. The magnitude of the frictional force on the Cheerios box is 2.6. Okay, and the magnitude of the frictional force on the Wheaties box is 4 Newton. If the magnitude of the applied force is 12.2. What is the magnitude of the force on this box from the Cheerios? Okay, what is your question here?
Yeah, the way that we solved this question is different from the way that I did. I want to take the force which was applied on the first box and then say this force minus the friction of the first box.
Yeah.
And then we'll get the force on the second box, which is applied by the first box.
Okay. So the thing is that here we are talking about the net force, first of all, right? Because the acceleration in this problem is coming from the net force. And the net force, when you are applying your force, that is one force, but you have the frictions coming from the two boxes. So those two frictions at once will be subtracted from your applied force, right? So therefore, you need to look for the net force, and that net force is creating the acceleration. So once you get the total acceleration, then you can go to the net force applied on the weighty sparks. Okay.
Yeah, but is it the net force that we want here, or is it the force applied from the first box to the second box?
It is the net force, because now you are talking about the acceleration, right? Because you're using the equation for the acceleration. The acceleration is always produced by the net force, not the total force coming from something, right?
Yeah.
So in that case, the force that is coming from the box number 1, which is the Cheerios, I guess. Yeah. When that force is coming, the fractional force of the second box will be also subtracted from that.
Yeah, if we take the acceleration of both of them together, like we're considering the net force here. If you can show the problem, Doctor, on the screen.
Okay.
I think it wanted the force from the first box to the second box, not the net force on the second box from the first box. This is what I understood from it.
This is we are saying it is the net force, okay? But the way in which they are saying it, they are not including, like you should be careful about this statement. First, when they say from the second box to the, right, they are not saying from the floor to the box. So the floor to the box, that force should be subtracted from it, so that you can see the coming from there, which is the net force. Yeah.
So I think if they specified, it would have been better, like if they want.
I think the statement is very clear as it is right now, but if they like a little more clarification can be made, like when you are saying the total net force on the second box. If they said there, then it will be more clear. Yes.
Yeah, but I don't see how you can derive from this what is the magnitude of the force on the Wheaties box from the Cheerios box that they want the net force. I mean, it just seems to me that the friction of the second box is just, it's not necessary to consider when we get the acceleration.
So you mean that here, like you're saying that we don't need to subtract this force, right? The friction force from the Wheaties box while it is in contact with this floor. That's what you said, right?
Yeah, basically what I'm thinking about it is, let's remove the second box, like for starters, and then just see the amount of force that the first box would do. And then
I think you're the thing what you are saying is,
and then get it from there, because that's like exactly the same.
Let's say you are talking about the total force, right?
I'm talking about the total force of the first box without the second box existing, and then I put the second box in the equation.
That's what they're doing. This is exactly how did you solve it, and how that's what they do. Right here, like in the formula, when you see it, f prime minus the fraction of the second weighty box equal to ma. You see it, right?
Yeah, but Yeah, go on.
Then they get it like you multiply this. You see 2.5 is the mass of the block times 1.44 is the
the second part makes sense.
So
Yeah.
which is 3.6, right?
Yeah, the
then,
second part.
Then you add the friction force with it, which is 7.6.
Yeah, the second part makes sense, but I'm talking about the first part. The first part, it took both.
It took both frictions because the acceleration in the combined system, it is created by the net force. It is not created by the total applied force. So if you are taking the total applied force and you look at the acceleration produced by that, the assumption that you are making that the two blocks are on a frictionless surface. So you are eliminating the frictions at all. So you will get a huge number for the acceleration, which is incorrect.
I removed the friction of the second in my estimation.
No. Okay, I'm getting into what you are saying.
Yeah.
Probably your mind is considering that the force should be applied to only one box, right?
My mind is considering we take one box, the first box, the small one, and then we see the net. Yeah, then we see the net force it's going to have, let's say to the right, and then we say that this force is the force which is applied to the box right next to it, even if it was, let's say, has a million friction, because it stays, this is the amount of force applied. Even if the box doesn't move, the force applied from the first box to the second box is still the same. It doesn't matter if the friction was high or low. So if we did the same way of thinking.
Let answer one thing. Let's say you brought two boxes. Okay. Initially, you are applying the force on the box number one. Will you be able to produce more acceleration in it with your force as compared to when you put the two boxes next to each other and then you apply the same amount of force? In which case will you get more acceleration?
Oh, the box alone, for sure.
Yeah, so when the box is only one box, then you will get produce more acceleration in there compared to when you have the two boxes next to each other and you are pushing on them. This is just because the two boxes are now in contact with the surface, and due to the friction, it is subtracting the force from your applied force, and therefore you are seeing, even though you are still applying the force on the box number two, but you cannot produce more acceleration in it, when it was alone.
Yeah.
So the thing is that if the way in which you are considering it, first of all, you need to look at the net force. So when you are having the net force, the acceleration is produced by that. Like in your case, you are completely eliminating the fraction from the second box when you are looking for the acceleration, which is not true.
Yeah, what I'm doing, doctor, is I'm trying to get to the point that when you say what is the force from the first box to the second box, it's different than the net force. This is what I'm trying to get at. Like the example that I gave.
I got your point. I got your point. When you are looking, supposedly you knew that the two boxes are going with some acceleration, they tell you. Then you do exactly what you said. Okay, this is exactly what you do, what you said. But the first step is only to determine the acceleration, and the acceleration is always produced by the net force.
Yeah.
So you did it that way.
Yeah, but you see, I see what you're saying very well, doctor, but like this is the example that I want to give. The second box, let's say, bear with me, I'm sorry, doctor.
Okay,
The second box, let's say that it was the heaviest box you can find. That box just will not move. And then there's the first box, we applied force on it, okay?
Yeah.
And the first box has some friction. So what I want to say is even if the second box does not move, there is force applied from the first box to the second box.
Yes, always.
So when we say that the acceleration is 0, we consider acceleration is 0 and we apply it to the second equation here, that would mean that there is no force from the first box to the second box if we apply that.
No. Then you will see that in the form of the fractional force, that will be static friction. And remember that in the static friction formula, there was a graph that the static friction increases initially, and then it goes to the peak point, and after that it drops a little bit to the kinetic friction. So when the two blocks are at rest, you definitely don't have any acceleration in that. But the force applied to the second box will be countered by the static friction.
Yeah.
Then you can still see in that. And the amount of that force which you are talking about will be exactly the same, but now the friction force is completely countering it. So the friction force and the applied force from the first block to the second will be there. You can see it.
Yeah,
It is
so when I think about it in this example, when I say the force of the first box to the second box, I'll say 0.
This is not 0.
And not the example specifically. I'm talking about the box that doesn't move example.
Yeah, so the force is not 0. That's what I said. The force will be equal to the static friction. Remember that there was...
Yeah. Okay. Yeah.
So the static friction is completely countering the force coming from the block A to the block B. So that is now matched.
Yeah. So if I wanted to get the force applied on them, what I do, you say, is use the static friction equation?
Exactly, yes.
I don't use the amount of force applied from, like, I'll use the mass of the first box and then the force applied on the first box. And then there's... Yeah,
go ahead.
I don't use the force on the first box and then the mass of it and then say that there's... and then subtract it from the friction. I'm sorry, I'll say that again.
Okay,
the force...
I got your point. Look at this equation. It is everything is here in this equation. You see the equation that I have highlighted here.
Yeah.
The example which you given me, that the two blocks are not moving at all. In that case, the acceleration is 0. Okay, you cross this out.
Yeah.
Now, how much force is getting into the second box? It will be your applied force minus the fraction produced A.
Yeah.
Which is equal to the static fraction in the second box. That's what you will see in that.
Yeah, so there is acceleration, but it's not actually moving because there is a force. So
yeah, because the acceleration will be 0 in that case, right?
Yeah, but if we considered, I guess, if there is a force there, there's an acceleration that doesn't really exist in the real world. Like there's an acceleration, that was discarded.
Yeah, because the net force, since the Newton law is about the net force. So the applied force is completely countered by all the static fractions from the opposite signs. Therefore, you are unable to produce any acceleration in it. So the acceleration is 0. Like, for example, you are attempting to move the wall, but you are unable to move the wall. So you're applying the force, some force on it, but the static friction of the wall is not allowing you to move it out.
Yeah, and so you see, this force that you're applying, it has some acceleration, I guess, because there's a force from your hand.
Because
right.
You can say in that, but it is completely hypothetical and doesn't exist in the real world. Like the way in which we are formulating the Newton's second law. First of all, think about the force. You have the force from one side you applied, and the wall applied another force on you, which is the static friction. If the force number 1 minus the friction force, if it was giving you some value, positive value or negative value, something, then you will have an acceleration. But
Yeah.
if force number 1 minus force number 2 is giving you 0, it means you produced 0 acceleration because the mass of the wall is always there.
Yeah, so I imagine it like this. There's like net acceleration and there's acceleration from each part.
You can do that, and certainly that is your way of approaching to it. I'm not disturbing that your mindset. But the way in which you are explaining it, it will become complex to the others because others will not understand. Others don't look at the accelerations first. Others look at the net force first and then look at the acceleration as a result of that.
Yeah, so the way that I imagine it in the hand wall example, you see this acceleration, which is not the net acceleration, it's the acceleration, the imaginary acceleration of the hand on the wall. I want to get the value of this times m to get the force from your hand to the wall.
Okay.
This is how I think it's solved.
It's fine, yes, it's also fine.
Yeah, so you see this way of solving, if we applied it on this,
if you apply this, your approach is not incorrect. It is correct approach. If you want to apply that and you want to see things in that way, it is one of the good approach. Yes.
Yeah, for some reason when I approach it that way and I try to get the hypothetical, I guess, force or acceleration from the first box, the way that I get that is from the example is that there is no wall, because when there's no wall and then you're just pushing on air, I guess, and then you go to the wall and then you push to the wall, it's better to think that there is no wall so you can see the net acceleration so you don't get confused.
Okay.
So on this example, I removed the second box.
Okay.
So when I remove the second box, I can get the acceleration of the hand, of the imaginary acceleration, which is going to apply on the wall or the box here.
That is creating the problem and some definite examples when you are talking about like the boxes. In that case, if you remove the second box altogether, okay, you are producing acceleration as a result of your force minus the kinetic fraction from the block number 1. It produced some acceleration, which is MA.
Yeah.
And that MA is hitting the second block, right?
Yeah. And this is exactly the force of the first box on the second box.
That's exactly true. That is exactly true. But we're here at this stage, like the problem as it is formulated, it is to the level of the current knowledge. Okay.
Yeah. The formulation, if you think about it, the formulation here.
The second way in which you are approaching to it, we are calling it impact. Okay. That will be impact, and that impact will come when you are colliding the two objects against each other. So there is another quantity, probably you may have heard about that, the momentum. You created a momentum and then you are trying to transfer your momentum from one object to another. So like in the Newton cradle, if you have seen that, it is exactly like that, and there's this called also the collision. So that will be the topics discussed when we begin our journey in the chapter 9 and 10 and so on. So those kind of discussions will come into that. Okay.
Yeah.
Based on the current knowledge and the current topics that we have been teaching the students, and assuming that the students have this level background, then we are not talking about the two objects separate and then they are coming and hitting each other. If we start to produce that, the complication is coming from the collision, and then there's momentum, and the momentum is transferred. So we have to bring a lot of more language into it, which will make the students a little bit confused. So we are not talking about those things at this point. So, but what you said, it is correct. You will see it's in the chapter 9 and 10, exactly in that way.
Yeah, so for this example, if I have the knowledge of momentum, I think you call, I don't know actually about momentum, but if I had this.
But that is your mind. That's what I am seeing now, because we are seeing the two blocks separate, and then you are transferring the impact of the one block to the second block. That is called collision.
Yeah.
And the momentum transfer. So you are actually, your mind is doing that thing already subconsciously. So we will get into that like in the chapter 9 and 10. Yes.
So if we had that, would my way of solving be correct?
It's perfect. It is perfect. No problem with that. As long as you're comfortable with that, just go ahead and keep solving that.
Yeah, for some reason it gives another answer if I did that way.
It will not give you a different answer because now you need to you are transferring the momentum, like when you take the two blocks separate, right? You created the initial block minus the second block, and then as a result of that, you are producing the acceleration, right? So that's the net force you are talking about, right?
Yeah, what I'm considering here is I want the force of this box on the second box, not the net. This is what I'm trying to get at. Like when you say I want the force of the hand on the wall, it doesn't have to do with the hand not moving the wall. What I care about is not the hand moving the wall or no. What I care about this acceleration that doesn't exist times m on the wall. So I can see you can hit the wall with 10 Newton or you can hit the wall with 15 Newton and the net acceleration would be the same.
The thing is that I can tell you this, just try to understand and bring yourself to the level of the subject, because the way in which you start to think about the hypothetical acceleration and everything, those approaches can give you the correct answer. But in the case of the wall in my hand, when I'm talking about my force on the wall and his reaction force from the wall is not actually moving. But if I'm saying that there is a hypothetical acceleration in things, the acceleration would mean that the object was somehow in motion. So when I bring the language of the motion, so I have the definition of the static friction. Now I need to call this static friction a kinetic friction. So the kinetic friction is different thing than the static friction. So everything, all the language, step by step, I have to change in order to put all the parts of the puzzle together. So what I'm trying to tell you is that when you are trying to apply your force, don't say it is an acceleration. Just say I'm applying a force, and there is a wall, and that is applying a reaction force on me. That is the friction force. So my force minus the friction force, if it gives me some value, then I will be able to push the wall and produce acceleration in it. If not, if this was not giving me some value, it was zero, then I will not be producing any acceleration in it. So I'm, with this context and this everything together, I'm in the completely my mind is in compliance with the textbook language.
Yeah.
Just stay in that language. That's what I'm.
I don't like the question, doctor. It's wrong. Okay. I think it's wrong, really. I think it's wrong.
No, the language is fine, but there is something which is puzzling you, which I don't know what is puzzling.
Okay.
There is another student. Are you waiting for us, Kautani?
Yes, mister. Can I ask something?
Okay.
Will you download the quiz 3 and the quiz 4 solutions?
Okay.
You will download it, or must I search about the questions?
You mean for you?
You downloaded quiz 2 before, after the quiz.
Okay.
When I searched about quiz 3 last week, I didn't find it, and I didn't found the time to ask you about it. But quiz 4 today, have one question that I didn't know really how to solve. So it will really help me to find the solution.
Okay, I can do that. Yes, I can upload.
Thank you, mister.
Yeah, no problem. Yeah. Okay.
Doctor,
Yeah.
I'm still not convinced by the question. Is that okay?
I'm saying that this question, it is fine. It is as it is fine, because the force is coming from the block A to block B, and that's all they're asking for.
Yeah.
But the initial force, when it creates acceleration, it is creating acceleration in the system, not in the single box, but the two blocks together. And therefore, the initial applied force minus the fraction coming from the block number 1 and minus the fraction coming from the block number 2. So when you take the net force, the applied force minus the two fractions, that will be your net force, and then you are creating the acceleration in the system, which is the mass of A plus mass of B times acceleration. Then you look for the acceleration.
Yeah. You know, I know how to solve this, but
yeah, everything is like that, but don't jump too much like that. The way in which it will be hard on you, because I can, if you ask me the question, I will be able to kind of give you the answer in that specific line of thoughts, because I don't want it to disturb the line of thoughts of a student. But you will find a difficult time, because all the textbooks and things, the definitions will be different. So your mind will be kind of trapped at one point. Yeah.
Like, for example, even when he says the frictional force, he doesn't specify the static or the moving friction. So that's why I thought I can use it even with the example of having no box, no second box.
The thing is that usually in such, okay, they are saying are accelerated across a horizontal surface by a horizontal applied force. So when they talk about the acceleration and later on they talk about the force, it should be understood that they are talking about the kinetic friction, because the object is obviously in motion.
I guess so.
Yeah, like in the figure here, the box of the Cheerios and the box of Wheaties are accelerated across a horizontal surface by a horizontal force applied to the Cheerios box. Okay, so then here there is acceleration. So therefore, it should be understood that the object is in motion.
Maybe if it wasn't at the start in motion, we'd have to divide it in two and then have one part where static.
If it was not given in the acceleration, then you have to determine whether under the action of the applied force, it will be able to move the object.
Yeah.
And then there will be two different coefficients of the fractions will be given, static and kinetic, and then you need to determine. So which will be kind of a lengthy problem. They don't want such problems to appear. And also I don't choose that kind of problems for the assignments either.
Yeah.
Yeah.
By the way, I skipped the class, so I might as well use my time here.
Okay.
Yeah. Usually, office hours, doctor, are in my other classes. Like, I'm supposed to have a class from 1 to 1:50. And
Okay.
for the Saturday one, it's the same thing. I have classes at the morning. So I have literally no time to ask you other than after class.
Okay. So after class times, I put the office hours, at least two of them after the office hours and one at other times, because some students usually have very adjacent classes after me, and then they cannot come into all office hours. But normally I found the office hours after the class more useful, because the students already stay with me and they continue their discussion.
Yeah.
So this is a little bit easy. If you ask the students to come at other time and join me, then it's become a little bit difficult.
Yeah.
Yeah. So anyway, just keep going. I think you got a good understanding of physics, and I think you are doing better. So just it's a physics. You need to kind of tune yourself a little bit.
It's physics, but sadly, it's just not complex enough, doctor. I just can't help myself.
It will get into complex parts after the chapter 8, because so far the things we have been studying, they were mostly studied in high schools.
Yeah.
So we grab the students from there, from the high school, and kind of push a notch up, high levels. But now, from now on, like when you are going towards the energies, and then the center of mass and moment of inertia and the rotational motions and all those kind of things. So it's kind of, now the students will have to kind of really pick themselves.
Yeah. I saw that, and I think I messed up today's test, so I can't really say anything about that one. I didn't have the time to study, I guess. I don't know. I didn't know, doctor. Wallah, I didn't know. And you haven't sent anything yesterday.
I
just checked.
I'm in the section 28, right?
Yeah. You haven't sent.
Okay. No, I sent. Let me tell you. Let me tell you this.
Let me share my screen.
Okay. Look at the section 28 quiz tomorrow. I just said quiz tomorrow. And then in the title I had, the quiz will be in class tomorrow.
Oh, on Outlook.
Probably on Outlook, because from here it should come to your
Blackboard.
From the Blackboard account. I don't know where your emails goes for the students. I don't know, but it was from the Blackboard, so it will go to your university email.
Yeah. No, I was on Blackboard. I haven't seen anything on Blackboard. Oh yeah, there it is from Outlook.
Yeah.
You should look at Outlook next time.
29 at that time also.
Yeah. So there's another problem on the what was it? On the same Wiley. The third one.
Okay.
I think it was like a car going.
A high-speed railway car goes around a flat horizontal circle. The rate is 400 meters at a constant speed. Horizontal and the vertical components of the force of the car on 65 kilogram passenger are this much. What is the magnitude of the net force of all the forces on the passenger, and what is the speed of the car?
Okay, so the first one is simple. Both forces we just
Take the components and take the right.
We take the ones that are horizontal and the vertical, because the car doesn't go up or down.
Yes.
Yeah. And then the second part, what is the speed of the car? I'm guessing we use the 2 pi r here.
It is going in the circle, and the speed is given, right? So you have the so there is this tension force, not the tension. Okay, so the speed is given. So from the speed you have the
Oh, okay. The acceleration is 0. No, it's not 0 because it's changing in direction.
It is v squared by r. It is a centripetal acceleration, right? Because the object goes in the circle.
Yeah.
So v squared by r you can use here.
But what's the acceleration?
Acceleration is v squared by r.
Yeah, we want to get the v. What is the speed? We want to get the speed, right?
Yeah, so that is the speed divided by r. The r is given here, right?
Yeah, the r is given, but the a isn't given.
The A is V squared by R, right? So you need to work for that.
Yeah. I don't have acceleration, and they don't have.
So you need to work for those components. That's what my guess is, right?
Yeah. I think maybe the acceleration I could get from centripetal force.
You got it, right?
I don't remember how I solved this one. I think I got the answer from internet. I'm not sure. I'm not gonna lie.
You don't need to get the answer from internet. You need to work on it so that you understand the problem.
Doctor, I had like an hour left. I didn't have the luxury.
Yeah, so anyway.
2 pi v.
Yeah.
Huh.
How did you do it?
I don't know, doctor.
Okay.
I'm puzzled.
Go around the floor horizontal cycle, so the radius is 400 meters at a constant speed. The magnitude of the horizontal and the vertical components of the force on a 65 kilogram passenger.
Oh.
So horizontal component of the force is already there, right?
Yeah.
So the horizontal component of the force is 212 Newton. And you are not looking at the vertical component of the force. So the horizontal component is considered centripetal force, which is m v squared by r, okay? You got the point?
Yeah. So 212
because
equals.
212 is mv squared by r.
But the m is of the car, and there's no m of the car.
No, this is given to us as the passenger. So we are talking about the passenger in this perspective, right?
Is it okay if we use
because the passenger in the car, both of them are going with the same speed.
Yeah, that's true.
Yeah, so we use that concept here, and then you look at the force given on the passenger, and then you kind of 212 times r divided by m, and you take the square root of this. So it will be 212 times r divided by m.
Yeah. No, it wasn't too bad.
Yeah. Times.
Though I want to see my grade. I might have gotten 0 for the first time in my life, doctor.
Really?
This is a moment. Yeah. I was panicking, doctor.
Yeah, this is exactly what we get. Something like that. Yes.
Yeah.
Okay.
I think the question is simple.
Okay.
It still doesn't give me my grade.
What?
It says late on the last quiz.
It is not giving you your grades?
No.
Okay. You mean the the quiz?
Yeah.
I need to go over this. So if we are done with the discussion, I will go over the quizzes and then assign the grades to students.
Yeah.
So this is release it. Okay. Yeah.
That's about it. Thank you very much, doctor.
No problem. Yes. Assalamu alaikum.
Can you solve mine first?